now time for me to introduce today's speaker, the last speaker of this term's seminar series. So today's speaker is Logan Hillberry, who is a PhD candidate in the Department of Physics at the University of Texas, Austin, under the supervision of Professor Mark Raisin. As an experimental physicist, Logan uses optical trapping, fast detectors, and data analysis to investigate thermodynamics at the microscale. Logan received his bachelor degree in 2015 and his master degree in 2016 from the Colorado School of Mines under the supervision of Professor Lincoln Carr. In Professor Carr's group, Logan learned about quantum mechanics and numerics through the study of quantum cellular automata, which indeed is the topic of today's talk. So Logan had an archive paper up, I think maybe a few weeks ago, maybe it's a few months ago now, on the topic, and you know, it's a super interesting kind of hyped up topic that we're very eager to learn more about. So with no further ado, please take over the virtual floor, Logan.
See. Hello, everyone. Thank you for that introduction, David. And it's really exciting for me to be here today and talk about some quantum cellular automata results with you all. And so, I'm sure everything is visible here. So the title of my talk today is Quantum Cellular Automata, Part 1. This Part 1 came from actually our March meeting talk just a couple of days ago. I had a colleague present on more quantum cellular automata results. And so we'll actually get Part 1 and Part 2 all rolled into one talk today. And the focus of today's content will be entanglement, physical complexity, and Goldilocks rules. And so to start us off here today, I want to talk about this idea of physical complexity. And so when I say the word complexity, that's the type of complexity I'm referring to. And more specifically, I won't be talking about algorithmic complexity, that is, say, the number of steps required to complete some algorithm, but nor am I just referring to some system which is complicated. Now, the complexity I am talking about really doesn't have a universally agreed upon definition, but I'll do my best to give you a sort of one-sentence flavor. And that is, complexity characterizes a system of multiple individuals which may interact in many ways, resulting in collective group behaviors. And so this is pretty abstract, but we can think of lots of examples from many disciplines which sort of fall into this paradigm. For example, if humans are our individuals, friendships make up our interactions, and those collective group behaviors are manifest over our social network. Another example, perhaps from the field of engineering, is, let's get my pointer here, is transistors making up the individuals, the conductive wires interconnecting them, making up their interactions. And then if you pile up enough of these transistors, a collective group behavior that's pretty interesting, of course, is the central processing unit. That's the thing that's letting me talk to you all today and present this talk, you know, and even perform these quantum simulations. So another important feature about all of these types of complex systems, or many of them at least, is that they balance trade-offs. For example, they'll balance trade-offs between generality and specificity. CPU, a central processing unit, is a very general computing, piece of hardware, but there's also the graphics processing unit, which is a little more specific. And then on the other side, there's also, say, a field programmable gate array, which is a very general piece of hardware with reconfigurable conductive interconnects between those switches. And another example of, a balance of a trade-off in a complex system is activity or stasis. And maybe an example of that is a single fish in a school of fish has to balance between working with the group and being an individual, going with the flow, or breaking away from the pack to try to get something to eat yourself. Now, an important abstraction in the complexity science world is that of network science. And in this abstraction, the individuals of the complex system are abstracted to the nodes of a network. Their interactions are modeled with some normalized weighted links between nodes. And then those collective group behaviors can be quantified by network measures calculated on those weights. And so a few examples could be node strength, which is just the sum of all of the weights on a node. And the distribution of node strengths can tell you about the presence of hubs in a network, that is, certain nodes which are more strongly connected than other nodes. An example of a network with a broad node strength distribution is a food web, where the individuals are species in an ecosystem, and their interactions, their network links, are formed by sort of who eats who. And because some food webs have these critical species, they serve as hubs in this network. And if they were to be sort of plucked from the network, they might cause, say, the collapse of the food web. Another example of a network measure is disparity. And disparity measures how much a network resembles a backbone. And an example of a highly disparate network is shown here. This is showing the metabolic pathways of biomolecules in a cellular organism, in a I think it was a hamster embryo. And so these large biomolecules can be broken up by the cell and used in lots of different cellular functions. And there's different ways that that sort of breakdown can go depending on what the cell needs at any time. And the resulting network has this backbone structure, which would be characterized as having a high disparity. Another example network measure is the clustering. And this measures how much the nodes in the network tend to form a tight-knit community. And an example network which tends to be highly clustered is that of a social network, where if I have two friends, it's likely that those two are friends themselves, sort of forming this transitive connection network of triangles. That type of motif in the network gives a large clustering to the network. And so with this sort of understanding of physical complexity that I've laid out here, but yet realizing, of course, I'm at this quantum information seminar, we're led to our motivating question today. And that is a very broad question and a very difficult one to answer. Does physical complexity arise in the quantum dynamical regime? And so we'll look at a few systems that tentatively answer yes to this question. And so our roadmap to getting to that answer will start with the classical cellular automata. And those are classical computing structures that are known to produce this type of complexity despite their simplicity. I will then show how to generalize these models to the quantum cellular automata that I will describe, and how certain quantum cellular automata rules called the Goldilocks rules balance a trade-off and in fact generate physical complexity. Moreover, I'll show that they do so quite generically by taking a few different generalizations, different options in defining and modeling and simulating those quantum cellular automata. And if there's time at the end, I'll look at possible physical implementations in a Rydberg atom system. And I'll close with some conclusions and an outlook for the future of this work. So let's get started by looking at some classical cellular automata. In these systems, the most simple version are called the elementary cellular automata, or ECA. And they are made up of a string of bits, or a bit string in one dimension. And the individuals are those bits, which can either be zeros or ones. Interactions of these bits are encoded into a local transition function. And so this function takes as input the state of some center bit and its two neighbors, and it gives as output the state of the center site in that neighborhood. Those local transition functions are simultaneously applied to all of the bits in the bit string, And then this process is repeated to generate time steps, and that will result in those collective group behaviors. So it turns out that with 3 inputs and 1 output for the local transition function, all of which can either be 0 or 1, there are 256 possible local transition functions, and we can simply enumerate them with the rule number R. And there's a coding of how R can be expanded into binary to determine exactly the form of that F. But I won't really go into those details right now because it's a little bit arbitrary. But the important thing is we can basically number all of the rules and then look at them. So let's look at a few examples. So the first example I'll show here is rule 90, and it generates this fractal known as Sierpinski's triangle. And we've initialized the system with just a single 1 in a sea of zeros and iterated the quantum cellular automata for several hundred time steps. Rule 30 is another interesting cellular automata, which is capable of generating encryption quality random numbers. And a final example I'll show here is rule 110, which is famously capable of universal computation. So some computers program and its hardware essentially can be programmed into the initial condition of this cellular automata, and sometime later its answer read out. So let's see how to make these models quantum cellular automata. The first natural thing is to trade bits for qubits. And so our discrete state space of zeros and ones becomes a continuous state space, say, of the block vector somewhere on or inside the block sphere. Next, we'll trade that local transition function for a double controlled unitary gate where conditioned on some left and right neighbors, will perform some operation, some unitary operation V on that center qubit. And we'll trade this simultaneous global update for an even odd site circuit layer type update. If we follow through this procedure, those 256 classical rules, which we'll distinguish with a capital C, become 16 quantum rules, which we'll distinguish with a capital T. The T reminds us that there are 3 qubits involved in the interaction, the center qubit, which is evolving, and the 2 neighbors, which will constrain that update. Later, I'll talk about the F rules for 5-site rules, and those will consider nearest neighbors as well as next nearest neighbors. And so we'll get to those a bit later. Let's take a closer look at this double controlled unitary gate and see where there's a trade-off which we might be able to balance to see if that generates physical complexity. And so this gate I've written out here, it consists of a sum over the local state space of the left neighbor and the right neighbor, and as well as this sort of matrix power thing happening at the qubit of interest, that center qubit. And so this CMN, this is a 0 or a 1, and that comes directly from the rule number. And so that's sort of how we do that encoding of dynamics to a rule number. It's related to these CMNs. But that means that this matrix power can either be the identity or that operator V itself. And so what we see happening here is that the neighbors decide whether or not that center qubit is static, we operate with the identity, or active, we operate with that operator V. So let's look at a few examples to build up an intuition here. Rule T0, in which all of the CMN are equal to 0, is trivially always static. It will just apply the identity operator to the center qubit without any respect for what the neighbors are doing. Similarly, rule T15 is always active. That is, it will always apply that operator V to the center qubit without any respect for what the neighbors are doing. Now, if we further constrain or allow updates, we arrive at what we might call these near Goldilocks rules, where there is some interesting constraining happening, either too much or too little constraining. So we might say too cold or too hot on those dynamics of that center site. And if we follow this procedure down to its balance point, we arrive at what we'll call the Goldilocks rule. And its definition is activate that center site, operate with that operator V if the neighbors are in opposite basis states. And so in addition to these rules that I'm showing here, the rules T1, 14, and 6, I'll also show the results for this rule T13. And that has a high activity like T14, so we might say too hot, but it also has this broken left-right symmetry. And as a result, it will exhibit behaviors that are the furthest from this Goldilocks case. And so these will form our initial sort of test cases for these QCA simulations that we'll be performing. And to give you a better idea of those simulations, what we do is initialize the system, and we'll consider 19 qubits. In each qubit is a 0, except for the center qubit, we initialize to a 1 for analogy to those ECA simulations I showed earlier. We set the boundary qubits to be zeros, so fixed boundaries. We choose as that local update unitary Hadamard gate, familiar from quantum computing. This is a unitary rotation which takes, say, the positive z-axis on the Bloch sphere to the positive x-axis. And we'll repeat this 2-circuit layer time step 10,000 times. And at each time step, record the state of the quantum system psi. So from that pure state psi, we can form a pure system density matrix, and then further trace out subsystems A of that system to create those mixed subsystems. From those reduced density matrices, we can calculate local expectation values. And we'll see later that this will give us an analog of the 0 or 1 visualizations that we saw in the ECA case. And we can also compute a quantum entropy to quantify entanglement between that subregion and the rest of the lattice. And here I'm showing the equation for the von Neumann entropy, which is what we'll use coming up here. So let's look at a few simple one-point observables in those QCA, which I've outlined. We see that it's the far from Goldilocks rule, T13, which quickly equilibrates to a high entropy value. So this is the local single site von Neumann entropy, starting with an initial 1 and a sea of zeros. It just evolves quickly to a high entropy state. We see there's a little bit of that left-right asymmetry that I mentioned in that propagation here. The near Goldilocks rules, T1 and T14, also appear to equilibrate, but maybe less quickly, and there seems to be some dynamics here at late times, very late times at the T1 rule. And then for the local expectation value of the poly Z operator, or the magnetization of the system, we see a similar story. And to conclude on this slide here, it's the Goldilocks rule, which we see has these interesting persistent dynamics even out to very late times. Now, to make the connection back to complexity science, let's make some networks. And to make a network, we will form the quantum mutual information between qubits J and K. And that's given by this formula here. It's the local von Neumann entropy of qubit J plus K minus the joint von Neumann entropy between qubits J and K. And this mutual information measure, we've given this factor of 1/2 here, which is non-standard, but it gives us that normalization to think of this M as a network of links. This quantity upper bounds 2 same time correlators in this quantum system, and the classical version of this metric has been used to quantify the complexity of signals in the brain. And so we're going to use it to look at our QCA. Now, an important thing about a complex network is that it's neither uniform, like this network of a GHZ state, nor is it random, like this network of some random state, some random point in Hilbert space. Instead, we see that our quantum cellular automata generate networks somewhere in between. And this rule T13, far from Goldilocks rule, looks the most like a random network. The near Goldilocks rules appear less random, and the Goldilocks rule T6 has this very unique structure, has some clear clustered groups of nodes, and it just visually stands out from the rest right away. So let's do some better quantification of these networks with some network measures. So the first one I'll look at again is this node strength. And I'm plotting here the distribution of node strengths over the entire system, as well as over late times in the evolution to build up statistics. And we see that the Goldilocks rule has an incredibly broad distribution, really underscored here on the linear horizontal scale on the inset. And that is signaling the presence of hubs in this network. So that is certain qubits which are highly connected to the rest of the qubits in terms of correlation based on mutual information. And then we also see just a clear delineation of the near Goldilocks rules, far from Goldilocks rules in random states. Next, we'll look at the clustering. We see that the clustering of the Goldilocks rule is significantly higher than all of the other rules and remains very dynamic out to late times. For disparity, we compute disparity as a function of time for these QCA, but further we compute the fluctuations of disparity. So the reasons we're interested in this is that disparity, remember, quantifies the resemblance of the network to a backbone. And so fluctuations in disparity quantify network reconfigurations. That is, how much the network resembles a backbone at one time compared to how much it doesn't at the next time will result in large fluctuations of disparity, signaling lots of network reconfigurations, showing that there's some sort of complex network dynamics going on. And we see that the Goldilocks rule is indeed undergoing the most disparity fluctuations. The far from Goldilocks rule less so, and the near Goldilocks rule T14 interestingly had this very slow decay of disparity fluctuations. We can show that these results are robust to system size. So as we increase up to 19 qubits, we see that the long time average of clustering and disparity fluctuations is stable or slowly decaying in the case of disparity fluctuations for the Goldilocks rule, whereas many of the other rules are quickly decaying. So another way we can connect back to complexity science is to look at entropy fluctuations. And so for this study, we're going to look at the second order Renyi entropy, so a slightly different quantum entropy. It still quantifies entanglement. It's related to the purity of a quantum system. But in particular, for the subsystem A, we're going to be interested in a bipartition. So we think of our quantum system cut near the center. And if you calculate the second order Renyi entropy for either of the systems, you'll get the same number. And so we think of this entropy as a property of the bond between the systems. And so we'll call it the bond entropy. And for the QCA that I've been talking about, again, we get these results for the bond entropy. We notice that the Goldilocks rule has the lowest overall value, but dramatically the largest variation. And so that's what we want to quantify in particular, again, is the fluctuations in entropy. And these fluctuations in entropy have been found to characterize macro scale complexity. In this paper here, they looked at fluctuations in entropy. I believe this was in the mixing of airways in mammal lungs, so related to biology. And also large fluctuations of disparity have been found at the order-disorder phase transition in a quantum easing model. And so we see that, again, the largest entropy fluctuations occurring for the Goldilocks rule suggest this balance between order and disorder and activity and stasis. And we take this high entropy fluctuation as well as the results of those network measures as signaling, indeed, this Goldilocks QCA rule 6, which we defined as balancing a trade-off, indeed does exhibit elements of physical complexity that we would associate to the large-scale world. And so from these results, we would like to show that they are somewhat general to specifics of the system. And so the first generalization I'll make is take the Hadamard gate, which we would operate on a site if the neighbors allow it, and replace it with a Hadamard gate times a phase gate. So that is a gate which rotates around the z-axis by an angle epsilon. Now, if we make this change, we can look again at the late time average of clustering, disparity fluctuations, and bond entropy fluctuations. And the story seems to be essentially the same. The Goldilocks rule maintains those highest complexity signatures for all angles epsilon. The far from Goldilocks rule, for the most part, is the lowest complexity generating state. Another generalization we can take a look at is initial and boundary conditions. So we'll look at boundaries fixed to zeros, as we already have, fix the boundaries to ones, or periodic boundary conditions. And as for an initial condition, we'll consider product states of ones and zeros, where a 1 is selected for each qubit with probability p, and otherwise the qubit is set to 0. We'll run that quantum cellular automata for a specific initial condition and store all of the subsystem density matrices that we're interested in, and then repeat that initialization simulation process 500 times and average all of those resulting subsystem density matrices. And from those average density matrices from the ensemble, we can compute all of the measures we've been interested in for complexity signatures. And so the results look like this. Again, for any of these columns, there's different boundary conditions. We see that the shape of the curve is largely the same for all of these boundary conditions. And along the horizontal axis for initial conditions, we see that, again, the Goldilocks rule maintains the highest signatures of complexity, except perhaps near the 50% probability. That's sort of the highest classical entropy of the initial condition. Shows a sort of a trade-off between the Goldilocks rule 6, the near Goldilocks rule T1 for, say, clustering. So we can also generalize our QCA to continuous time. And so in a continuous time type quantum system, like say a quantum simulator, we think of time evolution being governed by a global propagator, the exponential of some global Hamiltonian, where that Hamiltonian will write as a sum over some site local Hamiltonians, which we can connect to our QCA rules. And so to do so, I'll define a simple local state space projector and give it this letter P. And M here can be either 0 or 1 for the local state space. Then we can write this local Hamiltonian as some coupling between, states 0 and 1 with this poly X operator, and a sum, again, over projectors onto the left and right neighbors with a scaling of that same CMN, which is either 0 or 1. So this sort of turns on or off the constraint of certain neighborhood configurations, which will allow a state change. Now, in a classical computer, to simulate this type of global evolution, we'll often do a Suzuki Trotter decomposition. And if you follow through with sort of the simplest Trotterization of this system, it's neat that you end up exactly with the digital QCA protocol I've already been describing. But instead of a Hadamard local activation operator, you get this exponential of a poly X operator. So these two are very closely connected. And if we say run rule T6 in either analog or digital case, we get very similar dynamics shown here as the magnetization and clustering. And so what we deduce is that it's not so much about what you do to the center site, it's more about how you constrain it, how you allow that update to happen. And so if we have these continuous time QCA as one generalization, another generalization I already mentioned was moving to larger neighborhoods. And so these are what we call the F sub R rules. So if we use the same scheme to number our rules in the 5-site neighborhood, the combinatorics comes out to be about 65,000 rules. And so that's quite a bit to sift through. And so it's useful to pare those down a little bit to maybe find the interesting ones. And there's a clue hiding for us in how we think of the Goldilocks rule, which is the balance point of activating for an equal number of zeros and ones in the neighborhood. And so for a 5-site neighborhood, there's 4 neighbors, and the Goldilocks rule will activate that center site if 2 of those neighbors are ones. And so if we can say that, activate for 2 ones, that means we don't care about the placement of those ones. And that we can encode into a totalistic state space projector. And that means we don't care about the placement of the 2 ones. We sum over all of the permutations. So 1, 1, 0, 0, 1, 0, 1, 0, and so on. So if we enforce all of those permutations to be summed over, and then form a Hamiltonian which says, couple states 0 and 1 subject to a certain number of ones being in that neighborhood, we reduce to only 32 possible totalistic 5-site rules, which is a little more manageable. But of course, we're going to be interested, at least initially, in that Goldilocks rule, which in this numbering scheme is called F4. And I'll show a few of its dynamics here. Its network structure is reminiscent of Rule 6. It has this very interesting sort of clusters of 3 groups of nodes here. It has persistent dynamics, and it interestingly is pretty well localized in the center. Now, because it activates a site for 2 ones, the initial condition here is 1, 0, 1 in the center. And my advisor noticed this actually is reminiscent of another system. And this is an example of a breather in a waveguide array. And so in this physical system, there's very small optical waveguides separated by a few microns, so that as light is propagating through those waveguides, they can evanescently couple. And so you are essentially in this system having discrete in space optics and with nonlinear coupling. And these systems can support solitons. And if you excite 2 solitons into the system, they interact in this pattern called a breather. And sort of the visual analysis between, or similarity between these, has led us to call this system in the 5-site Goldilocks rule the entangled breather, which is a very interesting system. And we have lots of ongoing work to studying just this breather itself and building out that analogy between the discrete wave theory. And so another way we can think of kind of generalizing these QCA is there a physical system which could simulate them somewhat naturally? And we find that several of our Goldilocks rules can actually be simulated with Rydberg atoms. And so this setup is roughly like this. The 0 state is some ground state of a Rydberg atom, say rubidium-87, which has a very highly excited Rydberg state that can be coupled with, say, a globally addressed optical field for all of these Rydberg atoms. Maybe these atoms are optically trapped here, and their distance is a few microns. Now, since a Rydberg atom is such a highly excited state, it has a very large dipole moment, and that results in coupling between the sites through a van der Waals force. And so, and I also to mention that globally addressable fields can also be detuned in frequency from resonance. And so the Hamiltonian for this system looks like this. There's a term for the Rabi frequency term here, coupling the 0 and 1 states. There's a detuning term here, and this N operator is basically just the projector onto the Rydberg state. And there's a van der Waals interaction term here. And the important thing about this interaction energy is that it scales with distance as the distance between qubits to the -6 power. So it falls off very quickly, and that leads to these local interactions, which we can use to constrain updates to provide QCA-like behavior. And so all we need as external parameters turns out to be the detuning properly set to simulate various QCA. And so here are some of those results. For the one-dimensional or nearest neighbor T rules, we show rule T1 can be simulated with a detuning of 0, and the Goldilocks rule T6 can be simulated if we set the detuning to minus the nearest neighbor interaction energy. And so again, the dynamics aren't exactly the same. They're not perfect, as if we look at the sort of microscopic picture, we look at a few sites of this magnetization, and we see that a lot of the character is there, but some of the details are missing. The same is true for the Goldilocks case. Now, for the F rules, we have to be a little bit creative because there are 4 nearest neighbors. We can model this as a sort of quasi 2D system where each site J can indeed have 4 nearest neighbors that could all have the same interaction energy. And if we set the detuning to negative twice the interaction energy, we recover well this interesting entangled breather system with some slight differences in the oscillation frequency of the breather, the breathing frequency. But the interesting thing to me is that no matter sort of what we throw at these QCA systems, as long as we keep track of how those neighborhoods are being constrained, the QCA type behavior is robust. The microscopic details might change, but the complexity outcomes remain consistent. And so with that, I'll summarize with some conclusions here. The QCA, as I've defined them, are simple one-dimensional quantum systems. It's the Goldilocks QCA rules which balance activity with stasis. And it's those Goldilocks QCA which can reliably generate physical complexity. And so for some next steps in this project, we're interested in looking at integrability, chaos, and thermalization ideas in the context of our quantum cellular automata. And so we'll want to look at things like spectral statistics of the Hamiltonian and of the entanglement spectrum. And some initial results are very interesting in that it looks like the Goldilocks rules deviate pretty noticeably from the universal distributions. We can also look at page curves, which are like the bond entropy, but where we consider all of the possible bipartitionings of the lattice, and lots of other interesting measures to try to get a better handle on what's happening in the context of integrability, chaos, and thermalization, like ETH, eigenstate thermalization hypothesis, out-of-time ordered correlators, possible conserved quantities in this system. So there's a lot of interesting future work to be done here that we look forward to embarking on. And so since physics is never done in a vacuum, I would really like to thank my mentors and collaborators. Professor Lincoln Carr, my master's thesis advisor, gave me this really interesting project, several years ago, which has been very active for me ever since. My friends and colleagues, Matt and David from the School of Mines, helped me along the way many times. My colleagues, Patrick and Ning, really helped with early data analysis and interpretations of this system. And Nicole from that group as well has been a very useful mentor and advisor and astute observer of QCA dynamics. And our Italian collaborators, Simona's N and M, have been very useful in conversation, helped us dive into the physical implementations of Rydberg atoms and came up with that clever quasi 2D arrangement of the way of simulating the F rules. And of course, I thank you all for your engagement. And if you need more QCA in your life, be sure to check out our recently updated archive paper. And I would also be happy to take any questions that you have at this time. Thank you.
Okay, so thank you so much, Logan, for this very interesting talk. I can see that quite a few people dropped in the kind of first few minutes of the talk. So I'm going to repeat what I said in the beginning, which is that if anyone has a question they'd like to ask Logan, please just click the Q&A button at the bottom of the screen and write your name or say, hey, I have a question, and we'll promote you to a panelist and you can come onto the panel and ask your question live. So whilst people maybe contemplate whether or not they want to ask a question, I thought I'd get like a head start here, Logan. So I actually have a few questions, but maybe just I'll start with something very general, and then you can tell me if this is like a stupid question and you want to move on to something else. But you know, obviously, this kind of like limitation, like you have some physical system that evolves according to a very specific set of rules. This is how many people that kind of study the evolution of life kind of like start at looking at, like, you know, how did complex biology evolve from you know, just simple chemistry. And I was thinking, is there anything in your research or in your field of quantum cellular automata that relates that work to the potential of having quantum mechanical influence in biological systems? So is my question clear? So basically it seems your research is like, you know, what quantum rules would we have in order to have something useful and physically complex in a quantum system? And I guess that's what you would be looking for in biological systems as well.
That is an interesting question. And, you know, I think the answer might lie in sort of the answer to all of the is quantum relevant to bio thoughts is, I mean, you have to deal with decoherence at some point, and at some point the world becomes classical. An interesting thing we have found, though, is we've started applying noise to our simulations, trying to model them on maybe realistic present-day quantum computers. And we've been experimenting with possible sort of post-selection type algorithms on these noisy QCA outcomes. And interesting sort of new result that we're trying to understand right now is that while the quantum computer, you know, we're simulating it, it's becoming, it's decohering, yet if we apply this post-selection, our network measures no longer drop to zero, but they seem to be converging more to what we might think of as a classical complex network. And so somehow the combination of decoherence, but with our sort of, we want this to still be quantum post-selection mind, is driving the system towards a stable classical complex result. And not to say that that's maybe what's happening, you know, in the world, but it is a interesting avenue that we're continuing to explore, the combination of noise plus post-selection leading to not basically zero networks, but, you know, networks that remain high in clustering, but less dynamic.
Interesting. I see here in the chat that Mercedes asked, what was David's question? Sorry, audio stopped for a minute. I'll repeat my question and then hopefully people got the answer, which I think was a good answer. So my question was basically, can you use Logan's research or research within the field of quantum cellular automata to look at regions or regimes where quantum mechanics would be more likely to influence biological systems, for example? And I understand that, like, you know, questions of decoherence is probably the first thing to kind of address, so that makes sense. I see Alex, you have a question. Are you on the,
Yeah. Hi, Logan.
Hi.
I wanted to ask about this odd-even sort of interleaving of steps for the quantum case. Is this just something so that can be simulated, can be just expressed in terms of regular quantum gates, or why is there a difference from the classical automata?
Yeah, that's a good question. The reason it's different actually comes from, let me share these slides again. It was a little early. Let's see, it's the reason that we have to apply this even odd update is the following. In the classical case, it's a simultaneous update. And the way that that works is actually, it's sort of encoded in this little picture here. You have to have 2 copies of the bit string at any given time. You basically have to have one to read from and 1 to write 2. And so that means that, there's lots of ways in the numerics to implement this. You can just have a big array and you fill the bit strings 1 by 1, or you can have a copy. You can always keep a copy of the last state and then update the non-copy with the copy. And so in the quantum case, the argument is basically that we cannot create this initialize the quantum state and then run a QCA for a time step and then copy it to a register for arbitrary quantum states because of the no cloning theorem. And so with that, what we have to do is somehow time order the updates. And we've experimented rather than even odd, you can also just do a sweep right across the lattice, or rather than overlapping even odd, you can do, every third qubit, and then, so like 0, 3, so on, 1, 4, so on. Yeah, it's hard to say without writing out, a modular arithmetic. But yeah, so there's lots of ways to order these qubit updates. And it turns out that the symmetry of the resulting QCA changes, but its dynamical outcomes are consistent. So that's actually another way that we've generalized these QCA and seen the pretty much same results in terms of complexity outcomes.
Okay, so basically it doesn't really matter. Well, I was going to say that if you just simulate it numerically, you could just copy the wave function, I guess. But
of course, yeah.
As you say, maybe it comes down to the same outcome. So I was going to ask, because I was working on thermodynamics of spin chains with Nicole, whom you've credited. Do you see some parallel between a spin chain that is interacting with nearest neighbor interaction of some sort and this sort of automata, and how they, how magnetization?
Yeah, absolutely. And actually in our paper, the way we arrive at the Rydberg Hamiltonian and simulator that I described was actually sort of through an Ising model route. And it was sort of easier for us to think about the Ising model and constraining these updates, then make the connection to the Rydberg atoms, because the van der Waals force quickly decays. It can simulate essentially the Ising type system with certain parameter sets. And that's actually how we came to those parameter sets I was describing, was through a spin chain model.
Okay, thanks. Yeah, that makes sense.
Yeah, of course. And the details of that are in our archive paper if you want to check that out.
Okay. So I see that Mercedes has raised her hand. So I presume Mercedes has a question, and Hugo, my co-host, has also raised his hand, but I'll let Hugo deal with it himself. Maybe we should let Mercedes go first here.
Yeah, sure.
I can't see Mercedes nor hear her though.
Maybe I can go in the meantime then.
Yeah, go Hugo.
So I had this was a great talk, by the way. I had a question on scalability. So could you comment on the advantages and maybe challenges of scalability? You talked about this 3 rule where we're considering nearest neighbors, and then moving to a 5 rule obviously increased the complexity by quite a lot. So finding the actual Goldilocks rule was a real challenge, but it offered to model new dynamics and really interesting dynamics. Is there a reason for going even further and considering even larger systems of rules with 7 rules, 9 rules, or going to n rules? And obviously this makes things more complicated. Is this just unnecessarily complicated, or is there an advantage in doing so?
That's a good question. I would certainly be very curious. I mean, a dream of mine is to set up like some, machine learning AI to just explore the like 65,000 rule space, and, set that offshore on the 7 site neighbors as well, and say, look for interesting stuff. I mean, that's kind of one of the other definitions of physical complexity that scientists have tried to give, is you know it when you see it. And so maybe an AI can know it when it sees it. And I think there's definitely value in that in terms of scaling up to see what else is there. Another interesting direction is actually two spatial dimensions in which now nearest neighbors correspond to the 5-site rules, up, down, left, right, rather than nearest and next nearest neighbors.
Mhm.
And so that's another initial exploration we've done. And the issue there, though, is just, number of qubits we can simulate on our classical computer. I mean, it was pretty challenging to get 19 qubits and 10,000 time steps and all of these different parameters. It takes quite a long time, a lot of runtime. And in 2D, it's much worse to get enough space for something physically complex to happen. And so this is where we hope that some of these QCA will be simple enough to actually run on NISC-era computers, and that will be our scale up to see the interesting quantum phenomena.
Okay. And then
Sorry, no, Hugo.
to find these Goldilocks states, this is basically trial and error. You mentioned machine learning, which is some fancy trial and error to try to go and
And well, we formulated what we might call this Goldilocks principle, and that's predictive. It says no matter where we go in the neighborhood space, the Goldilocks rule is going to be the one that activates for a balanced neighborhood. So we knew right away which one we wanted to check in the 65,000 state space.
Right.
But actually, in a lot of cases, it's these near Goldilocks rules, which are almost equally interesting. And those are actually going to be perhaps the ones with a favorable gate count that we could actually simulate more sooner.
Yes. All right. Great. Thank you.
Mm-hmm.
I was just thinking with Hugo's question, like 19 qubits in density matrix formalism, this is a big thing, right?
That's right. So I said we formed the full system density matrix. That was more just to understand that we then take a partial trace, but numerically, we can actually just have the state vector of a pure system, then take that right to a reduced density matrix.
Okay.
The challenge is when we did multiple iterations, we had to at most have the half system density matrix. And
Right.
so that definitely is the thing that takes by far the longest.
Okay, I see Mercedes, I can now see you and hopefully hear you.
Hi, sorry, I was having I'm using two different monitors, so sometimes my mouse will hesitate to click. I just had one question. Thank you for your talk, by the way. What are the advantages or benefits of the Goldilocks QCA method, and how is it practicable, or how will it be practical foreseeably in the future, given that you mentioned that it exhibits the complexity in the description of biology, sociology, and economics.
Mm-hmm.
And also the different complexities when involved under the Goldilocks method. Is it a different kind of complexity than the other methods? Because if it's going to be complex science, I would assume that the automation is like still complex. So yeah, I guess that's still part of the advantage benefit part. But anyway, yeah, thank you.
Mm-hmm, mm-hmm. So one thing that has surprised me and fascinated me, that the Goldilocks rules, T6 and F4, that is both a 3-site and 5-site case, they have been actually so far some of the easiest to imagine physical implementations of. And so I guess I don't know what that means practically, other than demonstrating this in a physical system, I think would be a fascinating result to show that, yeah, actually we can go to the lab and find these signatures that we associate with large scale complexity in this, pure quantum system. Now, there's another element to the question of practicality, which is, what are these states? Where are they in Hilbert space, and are they useful? And there is some work done on that, as if we allow these QCA parameters, we don't strictly let them be the Goldilocks case, but we let them dynamically update in an iterative manner to try to drive the system to a specific state we're interested in. And there was a recent paper I'd be happy to share with you where they do exactly that. And so that could be actually a useful use of a quantum cellular automata, just like the history of classical cellular automata they are models of computation. That is, we can simulate, say, the Navier-Stokes equations using certain classical cellular automata on a hexagonal grid. So that actually follows through. A lot of the history of quantum cellular automata was focused on simulating certain equations like the Dirac equation, say, or lattice gases, quantum lattice gases. And so there is a lot of that practical side of QCA research in terms of what we can simulate and use them for, as well as what states do they generate.
But is that much different from using like density functional theory and looking at simulations and different codes like CASTEP?
So I think that in terms of the practicality, perhaps not. Though in terms of making that connection to physical complexity, it just felt a bit like a missing point in the QCA literature. QCA literature is pretty vast, but a lot of it is theoretical. It's about which QCA can simulate which QCA can simulate physical reality, which is a good practical question. But the classical cellular automata had sort of always been an archetype example of complexity, a very simple system of ones and zeros exhibiting diverse outcomes. And so we wanted to fill what we saw as a bit of a gap in that QCA literature and actually just ask the question and hopefully answer it. Does that complexity carry over to the quantum version of cellular automata?
Okay, and then when you were saying the advantages where you can do something in an iterative process, that was the advantage?
Yeah, and it's delocalized in a way. That's the advantage of classical cellular automata as well. Every neighborhood just sort of does its own thing. It doesn't have to have long-range connections. And so that in a way is a practical form of computation, especially in this early era of quantum computing where we have, for the most part, nearest neighbor couplings.
Really good, but the advantage?
I think that's the advantage, that it is simulatable, and therefore we would hopefully demonstrate physical complexity in a real world quantum system. You know, that's a fundamental science advantage. I mean, how practical it is, if that's up to one to decide.
Yeah, I would appreciate if you could drop the paper you mentioned in the chat, just so I can have a check out.
Oh, sure. Yeah, absolutely. I will.
Thank you.
Mm-hmm.
Okay, we're a little bit over the hour now, but if does anyone have another question, then we might stretch it a bit. I mean, I just out of curiosity, and this might not be your area of expertise, Logan, but like the first time I kind of heard about cellular automata was when Gerard 't Hooft, like the kind of renormalization Nobel laureate, gave a talk here in Cambridge many years ago, and he had this funky idea of explaining quantum mechanics via classical cellular automata. So some kind of, I guess, it's not really a hidden variable theory, but some super deterministic classical theory of quantum mechanics. Is this something that people in the field are still working on, or?
Yeah, I mean, in my view of the literature, it's a bit fractionated. There's a lot of things that are a QCA in certain ways, and a very recent review of QCA, 2019 and another in 2020, they both say something to the effect of they're all about like the formal definitions of a QCA, what makes a QCA, and at the end they say maybe a QCA is best defined as an infinitely repeating pattern of quantum gates. So that is definitely one idea of a QCA. 't Hooft's idea is another, I think, sort of completely separate camp. Like you said, can physical reality, including quantum mechanics, be described by some classical cellular automata? And in fact, then there's a whole third camp which use the term quantum cellular automata to refer to quantum dots, which are used to simulate classical cellular automata. So again, it's sort of this, how you arrange the quantumness and classicalness of your cellular automata gets you sort of these three different use cases of a QCA. And the bridge isn't super clear to me between the three camps, or if there is one.
Okay. I think, yeah, I think we're done with today. This was super interesting. I'm really happy we had you here.
Thank you. I really appreciate it. I appreciate the opportunity. It's an honor, really, and a big deal for me. So I'm happy to do it.